Welcome back. In this video, we're going to look at example problems of solving integrals using trigonometric substitution. Let's get to it. All right, so here's our first example. We have the integral of the square root of 2x squared minus 1 divided by x times dx. Now, when you want to solve integrals using trigonometric substitution, in most cases what you want to look for is a radical expression. And the form of that radical expression will determine which trig function you will use to substitute in order to solve the integral. And so here are the rules for using trig substitution. If your integral includes the square root of a squared minus u squared, where a is a constant and u is a function of x, then you want to substitute u for a times sine theta. If your integral includes the square root of a squared plus u squared, then you want to substitute u with a times tangent theta. And if you have the square root of u squared minus a squared, then you want to substitute u with a times secant theta. Now notice that this radical expression is very similar to what we have up here. The only difference is the order of a squared and u squared. And so if you have a constant minus a function u, then you want to substitute u with sine. But if you have the function minus the constant, then you want to use secant. And so an easy way to remember that is if the constant is first, you use sine, and if the function or the variable is first, then you want to use secant. So remember, constant sine, variable secant. So try to remember that phrase in order to remember the difference between what trig function to use for these two forms of a radical expression. But let's get back to our example problem. Notice that in our integral, we have the square root of 2x squared minus 1, and that is in the form of the square root of u squared minus a squared, right? We have some function of x squared minus a constant, which is what this form is right here. And when you have u squared minus a squared, and u squared is first, meaning the function or the variable is first, we will substitute in a secant function for u. Okay, but we need to determine what u is. If we rewrite our integral here, note that we could express it as the integral of the square root of 2 times x squared minus 1 squared, and that would still be divided by x and multiplied by dx. Right, if you square both of these parts, the square root of 2 squared is 2, and x squared is x squared, and so this is the same expression as this right here, just written more explicitly in a u squared form. And then we also have minus 1 squared, which is the same as 1 because 1 squared is 1, and so 1 squared corresponds to a squared, and so a is equal to 1. And so, if we set up our substitution here, remember we are going to set u equal to a secant function. In this case, u is the square root of 2 times x. So we will have that the square root of 2 times x is equal to a times secant theta. But remember that a is equal to 1. And so we're just multiplying by 1, which means that the square root of 2 times x will be equal to secant theta. Okay, so this is the substitution that we are going to make. And so if I clean up my work here, we can replace the square root of 2 times x with secant theta. And so if we do that, we will have that this is equal to the integral of the square root of secant theta squared minus 1, right? 1 squared is just 1, and that will be divided by x, but we don't want to write x anymore. We want to rewrite our integral in terms of theta, and so we need to replace x with what it would be equal to in terms of theta. And so if you go back to our substitution here, we can actually solve for x if we divide both sides by the square root of 2, and we would find that x is equal to secant theta divided by the square root of 2, and we could rewrite that to just be 1 divided by the square root of 2 times secant theta. And so that's what x would be equal to, and so let's replace that for x in our integral, and so in the denominator here, we will have 1 divided by the square root of 2 times secant theta. All right, and so then this would still be multiplied by dx. However, note that our integral is now expressed in terms of theta, and so we want to integrate with respect to theta, and so we can't leave it as dx. We need to express dx in terms of theta as well. We need a d theta. And so in order to get that, we will take the derivative of x with respect to theta. And so if we take the derivative of x with respect to theta, we will have that dx d theta is equal to 1 divided by the square root of 2 times the derivative of secant theta. Now the derivative of secant is secant times tangent, and so the derivative will be 1 divided by the square root of 2 times secant theta times tangent theta. All right, and then if we multiply both sides by d theta, we will have that dx is equal to 1 divided by the square root of 2 times secant theta times tangent theta d theta. And so now we can replace dx in our integral with that expression. And so I'll erase dx and we'll multiply by 1 divided by the square root of 2 times secant theta times tangent theta times d theta. Okay, and so now we have completely rewritten our integral in terms of theta, and so now we can simplify and then solve. And so if I clean up my work here, we can simplify and notice that we have 1 divided by the square root of 2 times secant theta in the denominator, but then we're multiplying by 1 divided by the square root of 2 times secant theta over here. And so we can actually cancel out those parts because they would just be divided by themselves, and so that's equal to 1. And so what we're left with is that this is equal to the integral of the square root of secant theta squared minus 1. That will be the square root of secant squared theta minus 1, and that will be multiplied by tangent theta d theta. So we'll have tangent theta d theta. Okay, and so if I clean up my work again, we can now simplify our integral further by noticing that secant squared theta minus 1 can be replaced with tangent squared theta via a Pythagorean identity. Right, remember one of the Pythagorean identities for trig functions is that secant squared theta minus 1 is equal to tangent squared theta. And so we can replace secant squared theta minus 1 with tangent squared theta to further simplify this integral. And so we'll have that this is equal to the integral of the square root of tangent squared theta times tangent theta d theta. All right, and now we have the square root of tangent squared theta, which will just be equal to tangent theta. And so this is equal to the integral of tangent theta times tangent theta d theta. And then we can multiply these two tangent theta functions together to get tangent squared theta. And so this is equal to the integral of tangent squared theta d theta. Now, if I clean up my work again, in order to integrate tangent squared theta, we're going to need to make use of that trig identity again, the Pythagorean identity, that tangent squared theta is equal to secant squared theta minus 1. And so this is equal to the integral of secant squared theta minus 1 times d theta. And now we can integrate each of these terms separately, because unlike tangent squared theta, we actually know what the integral is of secant squared theta. It's just tangent theta, right? The integral of secant squared is tangent. And then of course we can also integrate 1. It's just going to be equal to the variable of integration, which is theta. And so we'll have that this is equal to tangent theta minus theta, and then don't forget to add c. Okay, and so this is the solution to this integral in terms of theta. But remember that our integral is in terms of x, and so we want to find the solution in terms of x as well. And so what we need to do is rewrite our answer in terms of x. And so if I clean up my work here, in order to get our answer in terms of x, we need to know what tangent theta is equal to in terms of x, and we need to know what theta itself is equal to in terms of x. Now we can find all of that by working with our initial substitution. Let's first start by just finding theta. We can solve for theta in this equation by using the arcsecant function or the inverse secant function. Right? If we put both sides of the equation in an arcsecant function, so we'll have arcsecant of the square root of 2 times x, that will be equal to arcsecant of secant theta. The inverse secant function and the original secant function will cancel each other out to just be left with theta, and so we'll find that theta is equal to arcsecant of the square root of 2 times x. And so that is theta in terms of x, so we can rewrite that part of our solution. So this is equal to tangent theta minus arcsecant of the square root of 2 times x plus c. But now we also need to rewrite tangent theta in terms of x as well. And so in order to do that, we're going to need to make use of a triangle and how we can relate its sides to an angle using trig functions. All right, and so let me show you what I mean. If we draw a triangle here, where this angle is a right angle, and then another angle will be theta, we can relate that angle to the sides of the triangle using the acronym SOHCAHTOA. Right? The S stands for sine, the C stands for cosine, and the T stands for tangent. And what this tells us is that the sine of the angle is equal to the opposite side, which would be this side of the triangle, divided by the hypotenuse, which is the longest side of the triangle. Then it also tells us that the cosine of the angle is equal to the adjacent side, which is the side next to that angle, divided by the hypotenuse. And then for tangent, that will be equal to the opposite side divided by the adjacent side. And now in this case, in our original substitution, we used secant theta, which is not sine, cosine, or tangent, but remember that secant theta is equal to 1 divided by cosine theta. And so if we replaced secant theta here with 1 divided by cosine theta, the square root of 2x is equal to 1 divided by cosine theta. And then if we flip the numerator and denominator on both sides of the equation, we will find that 1 divided by the square root of 2 times x is equal to cosine theta. And so cosine theta for this triangle is equal to 1 divided by the square root of 2 times x, and cosine theta is the adjacent side divided by the hypotenuse. And so the adjacent side will be 1, so I'll label that with 1 for our triangle, and the hypotenuse is the square root of 2 times x, which will be the measurement for that longest side of our triangle. Okay, and then the side that we don't know, I'm going to label with b, and that is the opposite side. And we're going to need to know what that is, because in order to rewrite tangent theta in terms of x, we need to know the opposite side divided by the adjacent side. And so b is the opposite side that we need to determine. Now, if we use the Pythagorean theorem for the triangle, we know that the hypotenuse squared is equal to the other two sides squared and added together. So we have the square root of 2 times x squared is equal to 1 squared plus b squared. And so if we subtract 1 squared from both sides of the equation and square this term, we will have that 2 times x squared minus 1 is equal to b squared. And then if we solve for b by taking the square root of both sides, we will have that the square root of 2x squared minus 1 is equal to b. And so that is the measurement of the opposite side for our triangle. And so to rewrite tangent theta in terms of x, we will divide the opposite side by the adjacent side. And so the opposite side is the square root of 2x squared minus 1, and the adjacent side is just 1. And so we can rewrite tangent theta to be the square root of 2x squared minus 1 divided by 1. And that is tangent theta in terms of x. All right, and so then we can continue with our solution. We still have minus arc secant of the square root of 2 times x plus c. And this square root of 2x squared minus 1 divided by 1 is just going to be that square root. And so I'm just going to rewrite that, and we'll have the square root of 2x squared minus 1. And this right here is the solution to this integral in terms of x. Okay, and so that is how you solve this integral using trig substitution. Let's look at another example. All right, so here's our second example. We have the integral of 1 divided by the quantity x squared plus 1 squared times dx. Now, this might not initially look like an integral that we can solve using trig substitution. However, we can still use trig sub to solve integrals with rational powers. Right, so in this case, we have 1 divided by x squared plus 1 to the power of 2, or that quantity squared. And this can be compared to one of our forms of a radical function, which is u squared plus a squared. Right, we have a function of x squared plus a constant, and even though it's not underneath a radical, it still has a similar form to this form of a radical expression. And when we have this form, we want to set u equal to the tangent function. And so in this case, u is equal to x. And so we will have that x is equal to a times tangent theta. But a is just going to be equal to 1 because a squared is 1 and 1 squared is 1. And so a is just 1. And so we can multiply 1 by tangent if we wanted to. But in the end, our substitution is just going to be x is equal to tangent theta. All right, and so let's go through with the substitution and see if we can solve this integral. If we're going to let x equal tangent theta, then we also need to find dx. And so if we take the derivative of x with respect to theta, we'll have dx d theta is equal to the derivative of tangent theta, and that is secant squared theta, right? The derivative of tangent is secant squared. And then if we multiply both sides by d theta, we will have that dx is equal to secant squared theta d theta. Okay? And so let's substitute everything in to our integral here. This will be equal to the integral of 1 divided by x squared, but x is now tangent, so we have tangent theta squared plus 1, and that's squared, times dx, which is secant squared theta d theta. Okay? And so if we simplify, I'm going to move secant squared theta to the numerator of our fraction here. So this will be equal to the integral of secant squared theta, and that will be divided by tangent theta squared plus 1. That will become tangent squared theta, and so we'll have tangent squared theta plus 1 squared times d theta. And now if I clean up my work, we can use our Pythagorean identity to change tangent squared theta plus 1 to be secant squared theta. Right? If tangent squared theta is equal to secant squared theta minus 1, this is the same Pythagorean identity we used in the previous example, we can add 1 to both sides of the equation and have that tangent squared theta plus 1 is equal to secant squared theta. And so we can replace tangent squared theta plus 1 with secant squared theta. And so if we do that, this will be equal to the integral of secant squared theta divided by secant squared theta squared times d theta. Now we have secant squared theta divided by secant squared theta squared, and so this secant squared theta will cancel out with one of those in the denominator, and so we're just going to be left with the integral of 1 divided by secant squared theta d theta. All right, now remember, 1 divided by secant is equal to cosine, right? That's another trigonometric identity. 1 divided by secant theta is equal to cosine theta, and so 1 divided by secant squared theta will be cosine squared theta. And so if I clean up my work here, we can rewrite this integral to be equal to the integral of cosine squared theta d theta. All right, and now we have an integral that we are closer to solving. Now we have cosine squared theta d theta, and when you want to integrate just a cosine function to an even power, you want to rewrite that cosine function using a half angle identity. And so we're using a lot of trig identities here, and so it's important that you learn them and sort of internalize them as you work through more practice problems. In this case, we know that cosine squared theta is equal to 1/2 times 1 plus cosine of 2 theta, and that is the half angle identity for cosine squared theta. And so rewriting our integral with that identity will allow us to then integrate that function. And so this is equal to the integral of 1/2 times 1 plus cosine of 2 theta times d theta. All right, and so if I clean up my work again, we can pull this 1/2 to the outside of the integral, and this will be equal to 1/2 times the integral of 1 plus cosine of 2 theta d theta. And now we can integrate each of these terms individually, and cosine of 2 theta is going to require u substitution in order to solve. And so I'm going to split this integral up into two integrals. We'll have that it's equal to 1/2 times the integral of 1 d theta plus 1/2 times the integral of cosine of 2 theta d theta. And the reason we need to use u substitution on cosine of 2 theta is because it is a composite function. We will need to set u equal to that inside function and then rewrite our integral in terms of u. And so u will be equal to 2 theta, and if we take the derivative of that, du d theta will be equal to 2, right? The derivative of a variable to the first power is just equal to its coefficient, which is 2. And then if we multiply both sides by d theta, we will have that du is equal to 2 d theta. And whatever du is equal to, we need to be able to find that within our integral. But I don't see a 2d theta in here. I just see d theta. So if I divide both sides by 2, then we'll have that du divided by 2 is equal to d theta. And so now we can rewrite this integral in terms of u, But first, let me clean up my work. We will replace 2 theta with u, and d theta with du divided by 2. But first, let's solve this integral, and then we'll work over towards rewriting that in terms of u. And so we'll have that this is equal to 1/2 times the integral of 1, which is just going to be equal to the variable of integration, which is theta. So we have 1/2 times theta, and then we will add that to 1/2 times the integral of cosine of 2 theta d theta, but written in terms of u. So we'll have cosine of u times du divided by 2. Now if we pull that 1/2 to the outside, we'll have 1/2 times that 1/2, and so this will become 1/4, so I'll rewrite that as 1/4, and this will just be du. So we'll have du. Okay, now the integral of cosine is sine, and so this will be equal to 1/2 times theta plus 1/4 times sine of u, and then don't forget your plus c, and then we can replace u with what we set it equal to, which is 2 theta. And so I'm just going to erase that u, and we'll have sine of 2 theta. Okay, and so now what we have here is the solution to our integral, but in terms of theta. We're not quite done yet. We need to rewrite our answer in terms of x. And so let me clean up my work here again. We are going to need to determine what theta is in terms of x and sine of 2 theta. Now, if you watched my lesson video, you know that it's not going to be very easy for us to use a reference triangle with sine of 2 theta. And so we're going to need to use another trigonometric identity here to rewrite sine of 2 theta into a form that we can more easily rewrite in terms of x using a reference triangle. And that identity is this double angle identity, that sine of 2 theta is equal to 2 times sine theta times cosine theta. All right, and so working with sine of theta and cosine of theta is going to be a lot easier than working with sine of 2 theta, okay? And so let's rewrite our answer. This will be equal to 1/2 times theta plus 1/4 times 2 times sine theta times cosine theta plus c. And then 2 times 1/4 is 1/2, and so this is equal to 1/2 theta plus 1/2 times sine theta times cosine theta plus c. Okay, and so now this is the answer that we are going to work with and rewrite in terms of x. So let me clean up my work again. And let's start by solving for theta. We know that x is equal to tangent theta, and so that means that arc tangent of x is equal to theta, right? If we put both sides of the equation inside the arc tangent function, the inverse tangent function, or arctangent, would cancel out with tangent and leave us with theta, and so arctangent of x is equal to theta. So that's the first part of our solution. This will be equal to 1/2 times theta, which is arctangent of x, and then we will add that to 1/2 times sine theta times cosine theta. All right, now this is where our reference triangle comes into play. So let's draw our triangle. This is going to be a right angle, and then this angle will be theta. Remember the acronym SOHCAHTOA. In this case, we know what tangent theta is. It's equal to x, and so you could technically rewrite that as x divided by 1. And so if tangent theta is equal to the opposite side of the triangle divided by the adjacent side, then the opposite side is x, and the adjacent side is 1. So if we go to our triangle, the opposite side from the angle is going to be x, and the adjacent side will be 1. Now for the hypotenuse b, we're going to need that to write out sine and cosine, because sine of theta is the opposite divided by the hypotenuse, and cosine of theta is the adjacent divided by the hypotenuse. And so we need that hypotenuse, which I have labeled with b, but if we use our Pythagorean theorem, we know that b squared, or the hypotenuse squared, is equal to the other two sides squared and added together. So we have x squared plus 1 squared. And if we take the square root of both sides of that equation, we'll find that b is equal to the square root of x squared plus 1, right? 1 squared is just 1, and so b is equal to the square root of x squared plus 1. And so now, if we want to rewrite sine theta and cosine theta, we'll use SOHCAHTOA. Sine of theta is equal to the opposite side, x, divided by the hypotenuse, which is the square root of x squared plus 1. So we will multiply 1/2 in our answer by x divided by the square root of x squared plus 1. Then we'll multiply by cosine theta, which if we use SOHCAHTOA, cosine of theta is the adjacent side divided by the hypotenuse, and so we will have 1 divided by the square root of x squared plus 1. And so in our answer, we will multiply by 1 divided by the square root of x squared plus 1, and then we will add c. All right, and then to simplify our answer, note that the square root of x squared plus 1 is in the denominator of both of these terms, and so if we multiply them together, the square roots will cancel out, and we'll just have x squared plus 1 in the denominator, and that will be multiplied by 1/2, and so our final answer is that this is equal to 1/2 times arc tangent of x plus x divided by 2 times x squared plus 1 plus c. Okay, so these two square root functions multiplied together give us x squared plus 1, and then we multiply that 2 into the denominator, and 1 times x times 1 is x, and so x is in the numerator. Okay, and so this answer right here is the solution to this integral in terms of x. That's how we can use trig substitution to solve an integral with a rational power. Okay, let's look at one more example for this video. All right, so here's our final example. We have the integral from the square root of 2 to 2 of the square root of 4 minus x squared divided by x squared times dx. Now in this case, we have a definite integral, and so our trig substitution process is going to look a little bit different because now we also have bounds of integration to work with here. But the nice part is that when we rewrite our integral in terms of theta, we can actually convert our bounds of integration from values of x to values of theta as well, and so we will never need to convert our antiderivative back into terms of x. We will just be able to evaluate this integral at our bounds of integration in terms of theta. And so we'll get there, but first let's identify what we're working with here. We have an integral with a radical part, specifically the square root of 4 minus x squared, and that is in the form of the square root of a squared minus u squared. Now in this case, when you are subtracting a squared and u squared, and the constant a squared comes first, we are going to set u equal to a sine function. And so in this case, u will be x, and so we are going to set x equal to a times sine theta. Now a in this case corresponds to a squared, which corresponds to 4, and the square root of 4 is 2, and so 2 squared would be 4, which would be a squared, and so a is equal to 2, and so we can rewrite a to be 2. Okay, so our substitution is that x is going to be equal to 2 times sine theta. And so let's work with that substitution. We also need to find dx, and so we need to take the derivative of x with respect to theta. So we will have that dx d theta is equal to 2 times the derivative of sine theta, which is just cosine theta, and then multiplying both sides by d theta will give us that dx is equal to 2 times cosine theta d theta. All right, and so let's work with what we have so far to rewrite our integral. This will be equal to the integral from x equals the square root of 2 to x equals 2. Since we're going to be rewriting this in terms of theta, I want to make sure that we remember that our bounds are in terms of x. We did not convert them yet. And so we will have the square root of 4 minus x squared, but now x is 2 times sine theta, and so we will have 2 times sine theta squared, and then that will be divided by x squared, and so x is 2 sine theta, so we will have 2 times sine theta squared, and then we need to multiply by dx. Now I didn't quite give myself enough space to write that, but we will be multiplying by 2 times cosine theta d theta, this dx right here. Okay, and so let me clean up my work a little bit. There's our integral in terms of theta, except for our bounds of integration, which we are going to work on next. Okay, and so in order to convert these to be bounds of theta, we need to plug these values of x into our substitution equation and then solve for theta. And so let's start with our upper bound, x equals 2. If we plug that in for x in this equation, we will have that 2 is equal to 2 times sine theta. And if we divide both sides by 2, you'll have that 1 is equal to sine theta. Now if we take the arcsine of 1 and arcsine of sine, we will have that theta is equal to the arcsine of 1, and that will tell you that theta is equal to pi divided by 2, which makes sense because sine of pi divided by 2 is equal to 1. So our new upper bound for x equals 2 is theta is equal to pi divided by 2. And so I'll rewrite that upper bound. We will now have theta is equal to pi divided by 2. And now our lower bound is x equals the square root of 2. And so if we plug the square root of 2 into our equation here, we will have the square root of 2 is equal to 2 times sine theta. And if we divide both sides by 2 again, we will have the square root of 2 divided by 2 is equal to sine theta. Now I personally have this memorized, that sine of pi divided by 4 is equal to the square root of 2 divided by 2. But if you didn't know that, once again, you could take the arc sine of both sides of the equation, and that would cancel out with sine, and so you'd find that theta is equal to the arc sine of the square root of 2 divided by 2, which will give you the answer of pi divided by 4, and so theta is equal to pi divided by 4. Okay? And so that will be our new lower bound, and so instead of x equals the square root of 2, we will have theta is equal to pi divided by 4. All right, and so now by doing that, by converting our bounds to be values of theta instead of x, we will now be able to integrate this integral in terms of theta and then evaluate in terms of theta and get the correct final answer without ever needing to convert back into terms of x. And so this is going to be a lot easier than if we tried to keep working in terms of x. All right, and so let's simplify our integral and then integrate. We will have that this is equal to the integral from pi divided by 4 to pi divided by 2 of the square root of 4 minus 2 times sine theta squared. If we square each part, we will have 4 times sine squared theta divided by 2 times sine theta squared. That will also be 4 times sine squared theta, and that's multiplied by 2 times cosine theta d theta. Now, if we pull a common factor of 4 out of each of these terms underneath this radical, we'll have 4 times 1 minus sine squared theta, right? If we pull that 4 out of each term, I will just rewrite this to be 4 times 1 minus sine squared theta. Okay, so if you multiply that 4 back through, you would still have 4 minus 4 times sine squared theta, but now writing it this way allows us to see where we can make a simplification. 1 minus sine squared theta can be rewritten using a trigonometric identity, specifically the identity that sine squared theta plus cosine squared theta is equal to 1, and if you subtract sine squared theta from both sides of the equation, you have that cosine squared theta is equal to 1 minus sine squared theta. And so we can replace 1 minus sine squared theta in our integral with cosine squared theta. And so I'll do that here. I'm just going to rewrite that as cosine squared theta. And now by doing that, we can take the square root of each of these parts underneath this square root. We know that the square root of 4 is 2, and the square root of cosine squared theta will just be cosine theta. And so I'll rewrite that. We will just have 2 times cosine theta. Okay, and so now we have 2 cosine theta, and we also have 2 cosine theta out here. And so if we multiply that together, we will have 2 times 2, which is 4, and then cosine theta times cosine theta, which will be cosine squared theta. And so I'm just going to rewrite that. This 2 will become a 4, so we will have 4 times cosine squared theta, and then don't forget to write d theta. Okay, and by the way, hopefully you wrote out each of those steps in your own work if you are following along. The only reason that I just kept erasing and rewriting is so that I can keep explaining how to simplify this without having to waste a lot of time rewriting the integral over and over again. Okay, but now we're going to start rewriting it again. Notice that we have these 2 4s that will cancel out, and so we can rewrite this integral to be equal to the integral from pi divided by 4 to pi divided by 2 of cosine squared theta divided by sine squared theta d theta. All right, and so if I clean up my work here, we're almost ready to integrate, but first we need to simplify a little further. Remember, one of our trig identities is that cosine theta divided by sine theta is equal to cotangent theta. All right, so in this case, we have cosine squared theta divided by sine squared theta, and so if both of them are squared, then we can rewrite this to be cotangent squared theta. All right, so this is equal to the integral from pi divided by 4 to pi divided by 2 of cotangent squared theta d theta. Okay, but then we don't know a specific rule for integrating cotangent squared theta, but we can rewrite cotangent squared theta using another identity into a form where we do know how to integrate each term. Specifically, we're going to be using another Pythagorean identity that cotangent squared theta plus 1 is equal to cosecant squared theta. And so if you subtract 1 from both sides, we'll have that cotangent squared theta is equal to cosecant squared theta minus 1. And so we can rewrite cotangent squared theta in our integral with cosecant squared theta minus 1, and we will know how to integrate cosecant squared theta and negative 1. And so if I clean up my work here, we will have that this is equal to the integral from pi divided by 4 to pi divided by 2 of cosecant squared theta minus 1 times d theta. Okay, and so now we can integrate cosecant squared theta using one of our trig rules for integration. The integral of cosecant squared theta is negative cotangent theta. And then the integral of negative 1 is, of course, just going to be negative theta, because the integral of a constant is just that constant times the variable of integration, which in this case is theta. And so this will be equal to negative cotangent theta minus theta evaluated from pi divided by 4 to pi divided by 2. And so now if I clean up my work here, we are almost finished. We just have to evaluate this expression at pi divided by 2 and subtract the evaluation at pi divided by 4. And so this is equal to negative cotangent of pi divided by 2 minus pi divided by 2. And then we will subtract the evaluation at pi divided by 4. So we have negative cotangent of pi divided by 4, and then minus pi divided by 4. All right, now cotangent of pi divided by 2 is equal to 0 if you plug that into your calculator. And so this is equal to 0 minus pi divided by 2 minus negative cotangent of pi divided by 4. Now cotangent of pi divided by 4 is equal to 1 if you plug that in your calculator. So we'll have negative 1, because the negative in front of cotangent will make it negative, and then we will subtract pi divided by 4. And then if we distribute this negative through this quantity, this is equal to negative pi divided by 2 plus 1 plus pi divided by 4. All right, and so if I clean up my work here a little bit, negative pi divided by 2 plus positive pi divided by 4 is going to be negative pi divided by 4, because pi divided by 4 is just half of pi divided by 2. So if you add a positive pi divided by 4 to negative pi divided by 2, you're still going to be left with another negative pi divided by 4. So this is equal to 1 minus pi divided by 4, and that is the solution to this definite integral. Now, if you were to plug that into your calculator for an approximate value, it is approximately equal to 0.2146 and some more decimals, and so that is another acceptable answer to this integral. But either way, that is how you solve this definite integral using trigonometric substitution. When it's a definite integral, you don't have to worry about converting back into terms of x if you change your bounds of integration to be values of theta. All right, and so with that, this is the last example for this video. And so if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.